having me here to present this. So I'm a postdoc working together at X4 and at LTH. So we'll talk about this new sample delivery system that we have developed, mainly for aerosols, but also for nanoparticles, free, unsupported nanoparticles. To start with some acknowledgements, because this has been a team effort with people from Max4 and from people at Lund University. So the 5 of us have been working in a team for now about 2.5 years. 3 years. It's 3 years now. So it's Antti and Noel from Finest and FlexBest, and Noel is also a LDM coordinator, and Jenny and Axel bringing in their aerosol expertise, and we have the expertise from synchrotron radiation facilities that develop the new system. So it's been really a good teamwork these years. So this topic is about aerosol mainly. So that actually fits more into the environmental and climate research, but they're also something for new materials. So aerosols are basically airborne particles suspended in a gas, and these plays a huge influence in our for our health with exhaust particles and so on. But they also play a key role for the climate, as they are bring a lot of uncertainties to our climate modelings because of these particles that will form clouds and so on. But this talk will be mainly about synthesis of engineered nanoparticles that we can use an aerosol route to generate them. But we can also, it's also possible, I should emphasize that, to aerosolize particles from a colloid or colloid particles or something like that to study free particles without any substrate. So we're doing this in flight. So instead of collecting the particles onto a substrate, we have the particles already in an ambient gas or airborne in an aerosol system, and then we just letting the particles flow through, and the photon beam hits the particles without any substrate. So there are many advantages to doing this. We don't have any specific radiation damage because the particles are continuously renewed, and we can also know that there will not be any post-deposition changes. So if you're depositing the particles onto a substrate, you don't really know what's happening to the surface of the particles after depositing them and bringing them into vacuum. In terms of aerosol research, we also measure the true aerosol, meaning that we have particles and the gas simultaneously. And if you want to study how your generated particles are influenced by external conditions, such as heat, you can just change those parameters and then get an immediate response. But there are challenges, of course, to use this kind of system, and that is to achieve a high particle concentration in the photon beam during measurements. So we are doing measurements using X-ray photoelectron spectroscopy. All these things has motivated to develop this new type of system at X4. So this is what it looks like. You have the aerosol coming from here, and then you have the photon beam, and these two should intersect below the electron detector, the hemispherical analyzer, to collect the electrons that are excited from the particles. So the main advantage, the main challenge here is to bring the aerosol from atmospheric pressure to high vacuum in a continuous flow. And so the idea is that any users can bring their own aerosol generator and bring it just before our sample delivery system, and then the aerosol particles are letting into the system. So we had our first users in the fall of 2023, and they were measuring soot particles from a flame. You can see it on the bottom image here that they brought their soot generator, and they had an open flame in the hall, and then the particles are enter the system. So we measure the two particles. There's two beam times now, one in spring now, and we have two in fall of 23 it should be. But for the next for the fall of, okay, this is wrong, but for the fall of 2024, this year we have 7 new proposals. So it's increasing in attention, which is we're very happy about that. So we have studied engineered nanoparticles. I should mention that having like individual small nanoparticles are very difficult to study because they will start to diffuse before reaching the photon beam, and you will have a very diluted particle beam. But if you letting them agglomerate and form larger agglomerates, then these can be focused and brought to the photon beam with a high concentration. So we did this with engineered nanoparticles, studied different materials from aluminum, tin, copper, and zinc, and then managed to see that we can measure many different elements. So in this method, you're actually generating the particles in an aerosol system, but it should also be possible to just have a suspension of particles in a liquid and then just aerosolize it and measure it. Or if you're interested in droplets, if you have molecules in a droplet, that should also be possible, but we haven't done that yet. So we did a study now on surface reduction of tin using different carrier gases and also exposing these particles to different heating environments. So what we could see here was that by just changing the carrier gas during generation of the particles, we can also change the oxidation of the particles. So it has been known that by adding a few % of hydrogen to your carrier gas, it will form some kind of reducing environment and forming non-oxidized particles. But if we're looking at the surface structure, we still have an oxide surface. But this surface oxide can be changed by just increasing the number of the hydrogen amount. So as you can see here, by just going from a low amount of hydrogen into the carrier gas to a high, you change from a tin 4 plus dominant system to a more of a tin 2 plus. We also measured on the full size distribution and size selected nanoparticles just to see if that has any influence, but it showed the same trend. Then what we did next was to look at the high hydrogen content and then heat the particles in a tube furnace before reaching the sample delivery system. So you have the generation of particles, and then you have a tube furnace. And when you're heating the particles, these agglomerates of small primary particles, they will start to sinter at the same time and form more of a spherical shape. So these are about 60, 70 nanometers in size. At the same time, we can see that the surface oxidation also shifts dramatically, going from tin 4 plus and tin 2 plus, and then at intermediate temperature at about 700, you basically only have tin 2 plus, and then at 900 degrees, we're starting to see metallic tin on the surface as well. So if we plot all the temperatures all together, we can see how the trend in the different oxidation states changes with temperature. And this has been done for pure tin particles, but also for a mixture with tin gold particles. And we can see that the trends are similar, but it happens at different temperatures. So if we first look at the pure tin, the left case here, we see that we have a local maximum in the tin 2 plus, which then after a certain temperature starts to drop. And that is at the same time as we start to see the metallic tin on the surface as well. The same trend we can see with the tin gold. We have a local maximum in the tin 2 plus, and then it drops at the same time as we start to see the metallic tin on the surface. And the local maximum for the tin is about 700 degrees, but it happens at about 500 degrees for tin gold. So the gold in this alloy helps in the reduction, we guess, and we can see the reduction at the lower temperature than for the pure tin case. The last thing I want to mention is also that when we're doing these type of measurements, we always measure to vacuum because the particles are not on support. So they are free flying, and that means that we always include the electronic work function in our measurements. And so that means if the electronic work function of the particle changes, we will also see that. So in this case, you can see that the going from low temperature to a high temperature, the electronic work function shifting all the peaks with about 0.65 eV. So this can be used then to study the electronic properties of the particles and see how that changes as well. And we can see how it relates to the surface composition of the particles. So if we now look at how the electronic work function changes with temperature, you can see in both cases that it has a decrease, which is in agreement to what have been shown for similar measurements. But what we also see is that we have a local maximum in the work function at the same position, at the same temperature as we have the local maximum in the tin 2+ formation on the surface. And this is the same for the tin and tin gold case. And the decrease of the electronic work function with temperature can be of many reasons. For instance, changing the particle size, we're changing also, we may change the charge distribution of the particles, but also there could be some gas absorption and so on. So to summarize, we have developed this new system. It has been commissioned and it's open for user recently. And we still haven't tried everything that we want to do. We would like to study droplets and more advanced systems. But this one enables studies on aerosols and unsupported nanoparticles. And soon we will have our first method paper published. And with that, I want to acknowledge all the people involved and thank you for your attention.